the last section of this chapter, and we've just got 4 more sections in chapter 8 and we'll be done with this class. The last section in the chapter is not really learning a whole lot new. It's just putting our what we've learned into applications, modeling. Those would be word problems. So for example 1, it just wants us to solve for D. Well, that's not so bad. Let's get the 2, we'll put the 2 log of D on the left, and subtract 23.5 from both sides. So we've got S minus 23.5. Then divide both sides by 2. Okay, don't let that S bother you. And now we want to get the D by itself. Go back to the fact that this is log base 10 of D. So that means we can say that D is equal to 10 to the S minus 23.5 divided by 2. And yes, that is your answer. For example 2, solve for X. So let's start by adding T to both sides and divide both sides by 3. Then how do we get rid of an E? We natural log. So we have nx equals the natural log of 4.2 plus t divided by 3. Last, we're trying to get x by itself, so divide both sides by n. So we could write this as all that over n. In order to not make it look quite so complicated, I'm going to just write multiplied by 1 over n. It's the same thing. Times the natural log of 4.2 plus t over 3. Okay, so exponential growth and decay. If you have an exponential function and you have a positive constant, a positive exponent, then your model is growing. If your exponent is negative, then your function is decaying. Whatever you're modeling is decaying or decreasing. So for example 3, it says, suppose that at 19 years old, you win $100,000 playing the lottery. Oh, that would have been nice. If you would like to have $1 million when you retire at age 67, determine the average rate of return needed under continuous compounding. So the first thing is you need that formula for continuous compounding. It's A equals PE to the RT. So we want to get $1 million. So the amount we're accumulating will be 1 million. The amount we're starting with was 100,000. We know that this person is retiring at age 67, so we need to find T. You would just 67 minus 19 is 48. So T is 48, and we want to know R. So we need to solve this for R. Divide both sides by 100,000. and we're going to get 10 equals e to the 48r. Again, how do we get rid of an e? We natural log both sides. So 48r is equal to the natural log of 10, or r is equal to the natural log of 10 divided by 48. Put that in your calculator, we get 0.048. So the rate is 0.048 or 4.8%, which is usually how we talk about an interest rate, 4.8%. Example 4 says, according to a study published in 2012, Burmese pythons, that's a snake, are becoming the new top predator in the Florida Everglades. Oh, lovely. Not many animals in the Everglades can stand against a python that can grow 23 feet and weigh over 200 pounds. 20 pythons were recorded as captured or killed in 1995. By 2009, that number had increased to 378 pythons. Write a function of the form P equals P naught times e to the RT to represent the number of pythons captured or killed T years after 1995. So, we've got the formula that we're going to be using is however long in the future equals our initial amount times e to our rate of increase in this case times time. We need to know, first of all, what the time is. How many years are we looking at? So T would be from 1995 to 2009, subtract. That's 14 years. We were told that P of 14, in other words, the amount of pythons in 2009 is 378. We also know by creating a formula that P of 14 would be our initial amount of pythons, 20, times E to the RT. We don't know R, we know that T is 14. So we can set these, since they're both representing P of 14, we can set them equal. So we have 378 is equal to 20 E to the 14R. Then we just solve for R. So divide both sides by 20. E to the 14R will be 18.9. And then to get rid of the E, we'll natural log both sides. So 14R is equal to the natural log of 18.9. So R is the natural log of 18.9 divided by 14, which is approximately 0.21. What is that 0.21? Well, that is the rate of increase. So that means, in general, a formula would look like this. P of T equals our initial amount times E to the R, which we found to be 0.21, times T. So that way, now we have a formula that we can use to find the amount of pythons that should be in the area, in the Florida Everglades, at any point in the future. So part B says to use that formula to predict the number of pythons that will be captured or killed in 2017. Okay, so we're going to we can just plug in whatever T is for 2017. How do we find that? Well, the initial year was 1995, so we need to subtract that from 2017, 22 years. So we're finding P of 22. You can put that in the calculator, and we get approximately 2030. 2030 what? Snakes. Pythons. Oh, that just really wants me to visit the Florida Everglades. Now, Part C has us think about this. That is how many snakes, pythons, we can expect to get captured or killed in 2017. Granted, this book was written before 2017. So, that's a lot of snakes. But those are only the ones that are getting captured or killed. Not all of them. So, how many are there total living in the Florida Everglades if over 2,000 are getting captured and killed? Well, that's what Part C is going to talk about. If the ratio of pythons living in the wild to pythons captured or killed is approximately 100 to 1, how many pythons were estimated to be in the Everglades in 2012? Okay, so we're going back to 2012. And in 2012, T would be 17. So I'm going to go back and grab that equation again. So this time we're putting in 17 for T. And we get approximately 710. So there were 710 snakes, pythons, captured or killed in 2012. What does that mean about how many snakes there really were in 2012? Well, if the ratio is 100 to 1, and there were 710 captured or killed, multiply that by 100, that means there's 71,000 snakes, pythons that is, in the Everglades in 2012. Many more snakes that I care to think about. I think we need to get rid of some of them. Anyway, okay, so few more examples here. Example 5 says a sample collected from cave paintings on an archaeological site in France shows that only 2% of the carbon-14 still remains. How old is the sample? Well, when archaeologists are able to look at cave paintings or things from a long, long time ago, they use carbon-14 to decide how old it is. Okay, and however much carbon-14 is left helps them figure out how old it is. And so they use, in this case, this formula, Q at T, at whatever time, is equal to Q naught times e to the negative 0.000121 t, where Q0 is the original quantity of carbon-14. Well, we don't know how much carbon-14 was originally there. We weren't there, however many thousands of years ago. But we do know that 2% remains. Now, how they figure that out, I don't know. But 2% remains. So that means 0.02 of the initial amount, Q0, is equal to Q0 times E to this stuff, T. Since we've got a Q0 on both sides, Q0 goes away. So we've got this. We'll take that over to the next page so we'll have some more space. And now we solve for t. As usual, to get rid of a natural log, or get rid of an e, we'll natural log both sides. So we have negative 0.0000121 t is equal to the natural log of 0.02. Divide both sides by that negative very small number, and we get this, which, if put in the calculator, comes up with approximately 32,331 years. That means that cave painting was over 30,000 years old. That means that there were people living on the earth then. Anyway, that's a whole nother argument. We won't go into that. Okay. Logistic growth. Logistic growth is not logarithmic growth. Two different things, even though they both start with the log. If you think about exponential growth, okay, exponential growth looks like this. So I'm going to explain to you why logistic growth exists. Why do we do this? Look at that exponential function I just drew, the red one. Let's talk about bunnies. So, you've got bunnies living on an island. Bunnies like to make more bunnies. So these bunnies are going to reproduce and make lots and lots of bunnies. And so their population on this island is going to grow exponentially, right? And it's going to go up forever and ever and ever. And we're going to end up with millions and billions and trillions and gazillions of bunnies. No. The island is only so big. Let's say it's 4 square miles. So you can't fit billions and trillions of bunnies on 4 square miles, let alone the fact that there's only going to be so much food there for them to eat, and some of them are going to die and whatever. So, point being, exponential growth does not always work for our models. And so what we use instead is called logarithmic growth. Or, logistic growth. And what that looks like is this graph here, where we start off exponential, but then it evens out. At some point on that island, there is a maximum number of bunnies that can exist on that island and actually live and thrive there. Okay? At some point, they're not going to have enough food. They're going to start dying. You've got a limiting factor of how many bunnies can be there. So what we call that is the capacity. There's a capacity for how many bunnies can live in that island, and that is C. C is the capacity. So let's say that 100,000 bunnies could live on that island, then C would be 100,000. And if you graph C, if you graph y equals C, it's a horizontal line, then you can see that this equation, this logistic growth model, will get closer and closer and closer to that what is actually a horizontal asymptote. It will never reach it. So we'll never quite get 100,000 bunnies on that island. Okay, let's look at an example better than bunnies. Example 6 says, the population of Los Angeles, in millions, can be approximated by this logistic growth function. 3.194 over 1 plus 14.589 times e to the negative 0.052t. Okay. So, the first thing that I'm going to ask you is not on here, but what is the carrying capacity? 3.194. That's 3,194,000. So whoever this researcher was that came up with this problem decided that Los Angeles, the city of Los Angeles, could not support more than 3,194,000 people. So that is why the carrying capacity is that. But so we have this function, and here it is graphed for us. And part A says evaluate P sub 0 and interpret its context in this problem. So we'll talk about P sub 0 or P of 0 in a minute, but let's go ahead and figure out what it is. So on the bottom we have 1 plus 14.589 e to the negative 0.052, and that's where we plug in our 0 for t. And on the top is our 3.194. Put that in your calculator, and you get 3.194 divided by 15.589, or approximately 0.204888. What does that mean? Well, 0 was the initial year, and it says since the year 1900. So, since the year 1900, there were this many people in millions in 1900. There were this many people in Los Angeles. Transfer that to millions. That's 204,888 people in Los Angeles in 1990. Seems like a lot. Okay. On to part B. It says use this function to predict the population of Los Angeles on January 1st, 2016. So, we're just 2016. The 1st of 2016. So, find T to start with. We started with 1990, so we're subtracting that from 2016. That's 116 years. So we're going to use our function P at 116. So plug in 116 into our function. And we get approximately 3.09. So that means that there were we estimated there to be 3.09 million, not just 3 people, 3.09 million people in Los Angeles in 2016. Getting fairly close to our carrying capacity, isn't it? The last 2 examples are using logarithmic models for regression. Okay, so you're going to use Desmos, and I'll probably make you a Desmos video to go along with this. You may not need it, considering I've got the screenshots from Desmos on here, but we'll see. So we've got this data in our table, and it's been graphed for us, so we can see it looks exponential. How do we use Desmos to find the regression? Well, there are 2 options for an exponential model. Okay, notice this one says find an exponential model. Okay, important. So there's 2 options. One option, I don't have anywhere to write. We'll have to go back here. Would be something that looks like y equals ab to the x. The other would be y equals ae to the, what am I going to call that? I don't know. What does it call it over here? bx. So why are there 2 options? Well, both of these are exponential models. The first one is a typical exponential model where you've got a constant times something raised to x. And then the other one is an exponential model where you've got a constant times e to the something times x. So either of these would be exponential models. So to find these in Desmos, for the first one, just like you did when you were finding the regression for exponential or for linear equations, you put in your table up at the top, and then you say y sub 1. So here's our first one here. Y sub 1, and the little squiggly, a times b to the x sub 1. Okay, that's using our first model. And so we've been given these parameters where a would be that and b would be that. So our first option would be y equals 2.299 times 2.718 to the x. Our other exponential model, put it in y sub 1, squiggly, a times e to the, and you probably have to put this in parentheses as you're typing, b times x sub 1. And that gives you a and b for this one. So that would be y equals 2.299. Notice how the constant out front is the same. Times e to the 1.00013 times x. Which one matches better? Both of them r squared is 1, so either of them will work and give you the exact same answer. For example 8, this one is asking for a logarithmic model. For the logarithmic model, we're only going to use one option. It would be a plus b times the natural log of x. I'm not worrying about log, base, whatever. We'll just use natural log. So you would plug in, like here, y sub 1 squiggly a plus b times natural log of x sub 1. And that gives you a and b. So it would be 2.5031 plus 1.799 natural log of x. And that concludes section 3, 6, and chapter 3.